September 19th, 1943. Rechlin Experimental Airfield, Germany. Hauptmann Werner Baumbach lifted the olive drab metal housing from its shock-mounted cradle, the weight of the device settling into his hands with a solidity that spoke of precision engineering. The Norden Mark 15 bombsight, serial number 62412, had been carefully extracted from the nose compartment of a captured Boeing B-17F Flying Fortress 3 days earlier. Through the laboratory window, morning light reflected off the device's gyroscopes and optical components, revealing a complexity of mechanism that contradicted every assumption German intelligence had made about American bombing accuracy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Baumbach, a decorated Luftwaffe bomber pilot and technical officer with the Reich Air Ministry's Evaluation Division, had personally observed American bombing raids from the ground during attacks on German industrial targets. The precision displayed by B-17 formations, bombing from altitudes above 20,000 feet, had seemed impossible given the known limitations of optical bombsights. German doctrine held that accurate bombing required lower altitudes, where bombardiers could clearly identify targets visually. The Americans, however, were consistently hitting precision targets from heights that should have made such accuracy impossible. The device in Baumbach's hands promised to explain the mystery, though he could not yet comprehend how profoundly it would challenge German assumptions about the relationship between industrial capacity and technological sophistication. The bombsight had arrived at Rechlin as part of B-17F, serial number 42-30721, which had crash-landed near Munster on August 23, 1943. Following damage, sustained during a raid on German ball-bearing factories. The aircraft belonged to the 384th Bombardment Group of the United States 8th Air Force, based at RAF Grafton Underwood in England. Unlike most downed bombers that scattered their equipment across impact zones, this fortress had belly-landed in a field with sufficient control that the bombardiers' station remained intact. German recovery teams reached the aircraft before the crew could destroy sensitive equipment, discovering the Norden bombsight still mounted in its stabilized platform, its classified computing mechanisms fully accessible for the first time in German hands. German intelligence had pursued information about American precision bombing technology since 1941, when 8th Air Force operations began targeting occupied Europe from bases in England. Luftwaffe technical intelligence, working through multiple channels including human intelligence networks and analysis of captured equipment fragments, had established that American heavy bombers employed some form of advanced computing bombsight, but the actual mechanisms remained mysterious. Captured bomb fragments revealed specialized fusing, designed for precision strikes. Interrogation of shot-down bombardiers produced vague descriptions of automated aiming systems, though most captured crew members claimed ignorance of technical details, citing security protocols that limited their knowledge to operational procedures. Photographic reconnaissance of bomb damage patterns demonstrated consistency, suggesting automated fire control rather than individual bombardier judgment. These fragmentary clues pointed toward technological capability far exceeding anything German industry had fielded, but specifics remained elusive until the capture of intact equipment. The Norden bombsight, sitting on Baumbach's examination table, represented the culmination of more than 15 years of American development, though German engineers wouldn't immediately recognize the development timeline reflected in its construction. The device traced its origins to 1923 when Carl Norden, a Swiss-born engineer working for the United States Navy, began developing an automatic bomb aiming system. Norden possessed extensive experience with precision mechanical computing devices, having previously designed fire control systems for naval artillery. His insight was recognizing that bombing from an aircraft presented a ballistic problem fundamentally similar to naval gunnery, both requiring calculation of trajectory based on multiple variables including target motion, projectile ballistics, atmospheric conditions, and platform velocity. Throughout the 1920s and early 1930s, Norden refined his designs through successive iterations, each incorporating improvements based on testing and operational feedback. By 1933, the United States Navy adopted the Mark 11 variant for fleet use. The Army Air Corps followed in 1935, designating their version the M series. Continuous refinement through the late 1930s produced the Mark 15 variant that entered production in 1941. This was the version Baumbach now examined, representing the mature development of American precision bombing technology, incorporating over 15 years of engineering refinement and operational experience. The device measured approximately 24 inches in length, 14 inches in width, and stood roughly 12 inches tall when mounted in its stabilized platform. Its total weight approached 55 pounds, not including the stabilization mounting system that added another 30 pounds. These dimensions and weight immediately signaled to German engineers that American industry was willing to invest substantial payload capacity solely in bombing accuracy, sacrificing bomb load for precision capability. German bombsights, by comparison, weighed under 20 pounds, their simpler construction reflecting different design priorities that emphasized bomb capacity over computing sophistication. Baumbach carefully photographed the device from multiple angles before beginning disassembly, documenting the external configuration for reference during reconstruction. The housing consisted of aluminum alloy castings, precisely machined and finished to tolerances finer than standard German practice for non-critical aircraft components. Even the external case revealed manufacturing precision, suggesting automated production using advanced machine tools. German optical equipment housings typically showed hand-finishing marks, where technicians adjusted components to achieve required tolerances. The Norden's surfaces displayed uniform machine finishing, indicating American manufacturers possessed grinding and polishing equipment capable of achieving required tolerances without subsequent handwork. This seemingly minor detail carried significant implications regarding American machine tool capability and manufacturing automation levels. Opening the main housing required removing 6 securing bolts, each fitted with lock-wire safety provisions against loosening from vibration. The bolts themselves demonstrated remarkable consistency in thread pitch and head dimensions, suggesting they were interchangeable components manufactured to precise specifications, rather than individually fitted parts. German aircraft assembly frequently required mechanics to hand-select fasteners that properly fit specific holes, a time-consuming process that reflected looser manufacturing tolerances. The precision evident in something as mundane as mounting bolts hinted at systematic approaches to component standardization across the entire device. With the housing removed, the Norden's internal complexity became visible. The device contained over 2,000 individual components, including gears, bearings, gyroscopes, optical elements, and computing mechanisms arranged in a dense three-dimensional assembly. Each component occupied its position with minimal clearance, the tight packaging demonstrating sophisticated mechanical design that maximized capability within available space. German engineers recognized immediately that designing such complexity required not just individual component engineering, but systematic analysis of the entire mechanism as an integrated system, an approach suggesting American engineering methodology differed fundamentally from German practice of optimizing individual components separately. The heart of the system consisted of 2 gyroscopes mounted in precision gimbal assemblies that provided stabilized reference platforms independent of aircraft motion. The primary gyroscope, spinning at approximately 8,000 revolutions per minute, established a stable vertical reference against which all computations were referenced. A secondary gyroscope maintained directional reference, compensating for aircraft heading changes during the bombing run. German gyroscopic technology in 1943 could produce similar performance, but the Norden's gyroscopes demonstrated refinement in mounting and power systems that minimized drift over extended periods. Bearing surfaces showed extraordinary smoothness, their finish quality exceeding German military specifications for similar applications. The gyroscope motors employed brushless electrical systems that eliminated friction and wear issues inherent in conventional brush-type motors, a design sophistication suggesting American electrical engineering had solved problems German designers still struggled with in prototype development. Around the stabilization system, the Norden incorporated a complex analog computer that continuously calculated bomb trajectory based on multiple input variables. The bombardier manually entered airspeed, altitude, and wind conditions using calibrated knobs connected to gear trains. These inputs drove mechanical computing elements that physically represented mathematical relationships between variables. As the aircraft approached the target, the bombardier aligned crosshairs in an optical telescope on the aiming point, then engaged the automated tracking system. From this moment, the Norden's computer took control, continuously calculating the required release point based on current aircraft position, velocity, and bomb ballistics. The computing mechanism employed a series of precision gears, cams, and linkages that physically embodied the mathematical relationships governing ballistic trajectory. Each gear ratio represented a specific calculation. Each cam profile transformed one variable to another. Each linkage mechanically integrated multiple inputs to produce outputs driving other computing elements. Baumbach, examining the mechanism with growing astonishment, recognized the sophistication of the mathematical analysis required to translate abstract calculations into physical mechanism. Designing such a computer demanded not just understanding the mathematics of ballistics, but the mechanical engineering to implement those calculations using gears and linkages that would maintain accuracy under combat conditions, including vibration, temperature variation, and sustained operation over hours. The optical system integrated with the computing mechanism through a complex arrangement of mirrors, prisms, and servo motors. As the bombardier tracked the target through his telescope, the computing mechanism calculated the precise moment for bomb release. In the critical final seconds, the bombsight actually controlled the aircraft's flight path through an automatic pilot interface, making fine adjustments to heading that human pilots couldn't execute with sufficient precision. This level of automation surprised German engineers who had not realized American bombers incorporated automated flight control during bombing runs. German doctrine relied on pilot skill to maintain precise headings during attacks, a philosophy reflecting different assumptions about the reliability of automated systems versus trained personnel. Examining the servo mechanisms controlling the autopilot interface revealed another technological sophistication. The servos employed hydraulic amplification, converting small electrical signals from the computing mechanism into sufficient force to move aircraft control surfaces. This power amplification system demonstrated integration between the bombsight's computing elements, electrical systems, and the aircraft's hydraulic flight controls, requiring coordination across multiple engineering disciplines and organizational boundaries during development. German aircraft typically segregated control systems, with manual flight controls separate from bombsights and other equipment, a design philosophy that avoided complex integration but limited capability for automated operations. The bombsight's power requirements presented interesting evidence regarding American electrical systems. The device required 28-volt direct current power, which the B-17's electrical system provided through engine-driven generators. Total power consumption approached 400 watts during operation, a substantial electrical load that nonetheless represented only a fraction of the B-17's total electrical generating capacity. German bombers generated significantly less electrical power, their systems designed around more modest electrical loads. Dedicating 400 watts solely to bombing automation would have severely strained German aircraft electrical systems, requiring reducing power available for other equipment. The Americans apparently accepted these power demands as necessary costs for precision bombing, another indication of different priorities in system design. The optical components demonstrated manufacturing precision that equaled or exceeded the best German optical equipment. Lens elements showed exceptional clarity with minimal distortion across their apertures. Prism assemblies exhibited precise angles and surface finishes indicating sophisticated optical grinding and polishing techniques. Mirror surfaces displayed uniform reflective coatings applied with remarkable consistency. These optical components met specifications that German engineers recognized as demanding, requiring specialized manufacturing facilities and skilled technicians. That Americans could produce such quality optics in quantities sufficient to equip thousands of heavy bombers indicated manufacturing capability for precision components extending far beyond what German intelligence had estimated. Each gear in the computing mechanism showed similar precision. Teeth were cut with uniformity that ensured smooth, quiet operation across the full range of motion. Bearing surfaces displayed fine finishing that minimized friction and wear. Assembly clearances maintained tight tolerances throughout, preventing backlash that would accumulate errors in the computational chain. Baumbach and his team measured individual components, documenting dimensions and tolerances for comparison with German manufacturing capabilities. What they found consistently demonstrated that American production facilities achieved precision that German factories reserved for prototype or limited production items, suggesting systematic deployment of advanced machine tools across American war production. The stabilization platform, mounting the bombsight to the aircraft, incorporated sophisticated vibration isolation. Rubber bushings and spring assemblies damped high-frequency vibrations from engines and airframe, protecting sensitive gyroscopes and optical elements from disturbances that would degrade accuracy. The isolation system reflected detailed analysis of vibration spectra and careful engineering to provide isolation at frequencies that mattered while maintaining rigid mounting for low-frequency aircraft motions that needed to be transmitted to the computing mechanism. German engineers recognized this as evidence of systematic testing and refinement, suggesting American development processes included extensive prototype evaluation under realistic operating conditions. As German technicians documented the Norden's construction over subsequent weeks, patterns emerged, revealing American engineering philosophy. Every component showed evidence of design optimization, not for minimal weight or complexity, but for reliability, accuracy, and manufacturing reproducibility. Materials selection favored aluminum alloys and corrosion-resistant metals, despite their cost and machining difficulty, prioritizing durability over economy. Fasteners employed lock wire or self-locking nuts throughout, accepting the installation time required to ensure components wouldn't loosen in service. Electrical connections used gold-plated contacts and sealed connectors, preventing corrosion that might cause intermittent failures during missions. These design choices demonstrated American engineers prioritized performance and reliability over production cost or assembly speed, an approach that made economic sense only with confidence in vast industrial resources to support such intensive manufacturing. The most revealing evidence came from examination of vendor markings on components. The bombsight wasn't manufactured by a single facility but assembled from components produced by dozens of subcontractors across American industry. Gyroscopes bore markings from Sperry Gyroscope Company in Brooklyn, New York. Optical elements came from Bausch and Lomb in Rochester, New York. Electrical components showed origins from multiple manufacturers, including General Electric and Westinghouse. Precision gears carried markings from specialized machine shops in Connecticut and Massachusetts. This distribution of manufacturing across numerous suppliers indicated American war production had achieved integration across hundreds of facilities, each producing components to specifications sufficiently precise that parts from different suppliers assembled together without hand-fitting. German aircraft production relied heavily on vertical integration, with major manufacturers like Messerschmitt, Focke-Wulf, and Junkers producing most components in-house or working with small networks of closely supervised subcontractors. This approach provided direct control over quality and specifications, but limited production rates to the capacity of individual manufacturing organizations. The Norden demonstrated an alternative approach, where a prime contractor coordinated dozens of independent suppliers, each producing specific components to exacting specifications that ensured interchangeability. This horizontal integration enabled production volumes impossible for vertically integrated manufacturers, but required systematic standardization and quality control processes to ensure components from different sources assembled correctly. The technical manual captured with the bombsight provided another revelation. The document, designated Army Air Forces Technical Order 05-53A, contained detailed maintenance procedures, troubleshooting guides, and parts lists. Reading through the manual, German engineers realized American military doctrine expected field maintenance personnel to service and repair the complex bombsight using standardized procedures and replacement parts. Specific troubleshooting sequences addressed common failure modes. Parts lists identified replacement components by part number, with cross-references to authorized suppliers. Calibration procedures provided step-by-step instructions for verifying and adjusting the device's accuracy using portable test equipment. This approach contrasted sharply with German practice, where complex precision equipment required factory support for most repairs. German bombsights returned to manufacturer facilities for calibration and overhaul, a system that minimized training requirements for field personnel but created logistics, bottlenecks, and reduced equipment availability. The Americans apparently trained sufficient maintenance personnel and distributed enough test equipment that bombardment groups could maintain their bomb sites in field conditions, keeping more equipment operational and reducing dependence on rear area support facilities. This decentralized maintenance philosophy reflected confidence in their ability to train personnel to required skill levels and manufacture test equipment in necessary quantities, luxuries unavailable to German forces increasingly strained by multi-front war demands. Testing the captured Norden in static conditions revealed its theoretical capability, but raised questions about practical accuracy in combat. The device incorporated multiple sources of potential error, including gyroscope drift, gear backlash, optical alignment tolerances, input accuracy for airspeed and altitude, and environmental effects on mechanisms. Cumulative errors could potentially degrade accuracy significantly, yet American bombing results demonstrated remarkable precision against strategic targets. German engineers realized the bombsight represented only part of a larger system that included trained bombardiers, standardized operational procedures, mission planning methodology, and perhaps most importantly, the ability to fly in tight formation at high altitude where anti-aircraft fire posed minimal threat. The formation flying aspect proved particularly significant. Single aircraft using the Norden achieved good accuracy, but remained vulnerable to fighters and anti-aircraft fire. The American solution involved flying massed formations, where multiple bombardment groups released ordnance simultaneously when the lead bombardier toggled his release. This technique, enabled by tight formation, discipline, and inter-aircraft communication, concentrated bomb loads on specific targets while maintaining the defensive firepower of massed formations. The Norden made this practical by enabling the lead bombardier to aim precisely, while other bombardiers released on his signal, effectively multiplying the accuracy of one skilled bombardier across dozens of aircraft. German bombing doctrine had evolved differently, emphasizing individual aircraft bombing from medium altitudes, where visual identification of targets remained practical. This approach granted tactical flexibility, but prevented concentration of force and exposed bombers to greater anti-aircraft threat. Attempting American-style precision formation bombing required not just similar bomb sites, but years of training, institutional knowledge about formation procedures, development of appropriate tactics, and most critically, the air superiority that allowed American bombers to fly predictable courses during bomb runs without facing overwhelming fighter opposition. By late 1943, when German engineers examined the captured Norden, Luftwaffe bombers had been driven from daylight operations over defended areas, making high-altitude precision bombing academic, regardless of equipment availability. Hauptmann Baumbach completed his preliminary technical assessment in early October 1943, forwarding a detailed report to the Reich Air Ministry's Technical Intelligence Directorate. His conclusions proved sobering for German leadership, expecting to find exploitable weaknesses in American technology. The Norden bombsight, he reported, represented a mature development, incorporating sophisticated engineering across multiple disciplines, including mechanical computing, precision manufacturing, gyroscopic stabilization, advanced optics, and automated controls. American industry had clearly invested enormous resources over many years, developing precision bombing capability, demonstrating long-term strategic planning and technical competence that German intelligence had significantly underestimated. More troubling than the device's sophistication was the manufacturing precision evident throughout its construction. The consistent quality and tight tolerances indicated American war industries possessed machine tools and production capabilities exceeding German industry's ability to match in their current strained circumstances. If bombsights represented typical American precision manufacturing standards, then American war production generally achieved levels of quality and consistency that German factories struggling with material shortages and skilled labor depletion couldn't approach. This implied that quality differences favoring American equipment would persist regardless of German efforts, since closing the gap required not just copying designs, but matching entire production systems, including machine tools, materials, and skilled workforce. The report circulated through various Reich Air Ministry departments, generating responses that revealed divisions within German technical and military leadership. Some officers dismissed the bombsight's significance, arguing that German bombing accuracy at lower altitudes, using simpler equipment, achieved satisfactory results without complicated mechanisms. Others recognized the strategic implications, noting that American ability to bomb accurately from 25,000 feet neutralized German anti-aircraft defenses optimized for lower altitudes. Still others focused on the manufacturing evidence, warning that consistent precision across American war production indicated industrial capabilities that Germany, already struggling with resource constraints by mid-1943, could never match through any realistic mobilization plan. Reichsmarschall Hermann Göring, Commander-in-Chief of the Luftwaffe, received briefings on the captured bombsight in November 1943. His response revealed the cognitive dissonance affecting German leadership, increasingly confronted with evidence of material inferiority. Göring acknowledged the Norden's sophistication, but insisted German industry could produce equivalent equipment if properly directed and resourced. He ordered development of an indigenous German precision bombsight matching American capability, seemingly oblivious to the reality that German aircraft production facilities, already struggling to maintain fighter output under sustained Allied bombing, lacked capacity for major new development programs requiring years of refinement and specialized production facilities. The order to develop a competing bombsight made its way to Carl Zeiss, Germany's premier optical and precision instrument manufacturer, and to various aeronautical research institutes, including those at Rechlin. Engineers assigned to the project immediately recognized the impossibility of matching American capability within any time frame relevant to the war's outcome. The Norden represented 15 years of continuous development, involving thousands of engineering man-hours, extensive testing programs, and systematic refinement of manufacturing processes. Germany, in late 1943, lacked both time and resources for such comprehensive development, even assuming no Allied interference with research facilities and production sites. Some preliminary work proceeded regardless, producing paper designs for automated bombsights, incorporating gyroscopic stabilization and mechanical computing elements similar to the Norden. But these designs never progressed beyond prototype stages. Germany's critical shortages of strategic materials, limited availability of specialized alloys required for precision mechanisms, machine tool capacity already fully committed to producing existing weapon systems couldn't be diverted to manufacturing complex new equipment. Most significantly, Germany's deteriorating strategic situation by 1944 made precision high-altitude bombing irrelevant to Luftwaffe requirements, with Allied air superiority preventing daylight bombing operations and forcing remaining German bombers into night harassment missions against tactical targets. Investment in precision bombing technology made no operational sense regardless of technical feasibility. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Norden bombsight's revelation extended beyond its immediate technical sophistication to implications about American industrial organization and strategic planning. German engineers, examining the device, recognized it represented not an isolated achievement, but evidence of systematic approaches to military technology development. The United States had identified precision strategic bombing as a doctrinal requirement more than a decade before the war. allocated resources for comprehensive technology development, refined the capability through extensive testing and operational experience, and scaled production to equip thousands of heavy bombers with mature technology at war's outbreak. This sequence demonstrated strategic planning horizons and resource commitment that Germany, despite its reputation for technical prowess, had failed to match in most military technology areas. The contrast with German bomb development highlighted differences in military-industrial organization and planning processes. Germany had developed effective precision bombsights for specialized purposes, including the Luftwaffe 7C used by Stuka dive bombers and specialized equipment for naval torpedo bombers. But Germany had never committed to strategic high-altitude precision bombing as a doctrinal requirement, consequently never investing in developing comprehensive capability comparable to American approaches. This reflected different strategic doctrines, with German air doctrine emphasizing tactical support for ground forces rather than independent strategic bombing campaigns. But it also revealed German military planning's shorter time horizons, focusing on immediate operational requirements rather than developing capabilities requiring years of sustained development. By spring 1944, the captured Norden had been thoroughly documented, its secrets extracted and circulated through German technical intelligence networks. Several additional Nordens had been captured from other downed B-17 seconds, allowing comparative examination that confirmed the initial findings about manufacturing consistency and quality. The devices found their way to various research institutes and training facilities, where they served as teaching tools demonstrating American technological capabilities. But this knowledge provided little practical benefit to German forces already overwhelmed by Allied material superiority across all domains. The bombsight represented a small but symbolically significant piece of a larger pattern, German engineers increasingly recognized as they examined captured American equipment throughout the war. Whether analyzing Sherman tanks, P-51 Mustang fighters, proximity-fused artillery shells, or countless other items, German technical experts consistently found evidence of superior manufacturing capabilities, systematic design approaches, and resource availability that Germany couldn't match. Individual German designs often showed greater sophistication in specific technical areas, but American equipment exhibited consistent quality, reliable performance, and most importantly, availability in overwhelming quantities. This quantity versus quality dynamic fundamentally determined the war's material outcome. Germany produced technically advanced fighters like the Messerschmitt, Me-262 jet fighter, and sophisticated precision weapons, including guided bombs and missiles that represented cutting-edge technology. But these advanced systems arrived in insufficient quantities too late to affect strategic outcomes, while simpler American equipment flooded battlefields in numbers that rendered technical sophistication irrelevant. 1,000 adequate bombers using automated bombsights could accomplish what no dozen technically superior aircraft could achieve, and America was building those 1,000 bombers monthly, while Germany struggled to replace losses from existing production. The Norden bombsight examinations at Rechlin during late 1943 and early 1944 coincided with a broader recognition among German technical and military leadership that the war had become unwinnable through any realistic means. The steady drum of bad news from all fronts, the increasing devastation from Allied strategic bombing, the overwhelming material advantages demonstrated by captured equipment, all pointed toward inevitable defeat once Allied industrial capacity fully mobilized and deployed. Officers and engineers who understood the implications faced difficult choices between speaking unpleasant truths to leadership, unwilling to hear them, or remaining silent while the Reich marched toward catastrophe. Some chose silence, focusing on immediate technical tasks while avoiding larger strategic questions beyond their authority. Others attempted to communicate uncomfortable realities through carefully worded technical reports, emphasizing capability gaps and recommending unrealistic remedies they knew couldn't be implemented, thus documenting their professional objections for potential post-war scrutiny while avoiding direct confrontation with leadership. A few spoke plainly about Germany's deteriorating position, sometimes facing career consequences or worse for undermining morale with defeatist assessments. The Bombsight reports joined hundreds of similar technical evaluations circulating through German military bureaucracy, collectively painting a picture of comprehensive material inferiority that senior leadership preferred not acknowledging directly. The Norden's computing mechanisms particularly fascinated German mathematicians and computing specialists brought in to analyze the device's mathematical principles. The Bombsight represented a special-purpose analog computer designed to solve specific ballistic equations continuously during flight. By embodying mathematical relationships in physical mechanism, American engineers had created a device that performed calculations faster and more reliably than human operators could achieve with slide rules and tables, even when those operators possessed exceptional mathematical skills. This principle of mechanizing computation for military purposes suggested broader applications across fire control, navigation, targeting, and other domains where rapid calculation provided operational advantages. Germany had developed some analog computing devices for specific military purposes, including advanced fire control computers for capital ships and sophisticated targeting systems for certain weapon systems. But American implementation of computing principles in something as tactically specific as bombsights indicated systematic application of computing technology across their military establishment, another evidence point suggesting organizational approaches to military technology that differed from German methods. The captured Norden prompted discussions among German computing pioneers, including Konrad Zuse, about potential applications of automated computation to military problems, though these discussions led to little practical development given Germany's resource constraints and limited timeframes. The optical telescope integrated into the bombsight demonstrated refinement that impressed even German optical specialists familiar with Zeiss's renowned products. The telescope provided approximately 3 power magnification with exceptional clarity and minimal distortion across its field of view. More impressively, the optical system maintained calibration despite aircraft vibration and temperature variations that might affect lens mounting or alignment. This environmental stability reflected careful design of the mounting system and selection of optical materials with matched thermal expansion characteristics. German optical equipment matched or exceeded this performance in laboratory conditions, but achieving similar reliability in field service under combat conditions, while maintaining production rates sufficient for thousands of units, indicated manufacturing sophistication beyond just optical grinding expertise. The bombsight's sighting head incorporated clever mechanical features for target tracking that revealed attention to human factors and operator ergonomics. The bombardier manipulated control knobs that felt natural and intuitive, with appropriate resistance and smooth rotation that facilitated precise adjustments without requiring excessive force. Visual displays used clear markings and logical layouts that minimized opportunities for operator error. Emergency backup procedures allowed manual bombing using optical reticles if electrical systems failed, providing degraded capability rather than complete failure. These human factors considerations throughout the design suggested American developers included extensive operator testing during development, refining interfaces based on feedback from actual bombardiers rather than purely theoretical analysis by engineers. Examining the servo mechanisms revealed sophisticated electrical and hydraulic engineering that enabled automated flight control during bombing runs. Small electrical motors controlled by the computing mechanism drove hydraulic valves that directed pressurized fluid to actuators moving control cables. This power amplification system allowed the relatively weak electrical outputs from the computing mechanism to control aircraft heading with sufficient force to overcome aerodynamic loads on control surfaces. The servo system incorporated feedback mechanisms that sensed actual control surface position and compared it to commanded position, automatically adjusting hydraulic flow to minimize error. This closed-loop control represented advanced control theory implementation requiring sophisticated understanding of system dynamics and stability. Mathematical principles that German engineers recognized but had not systematically applied to automated flight control systems. The autopilot interface between bombsight and aircraft systems required standardization of control protocols and signal formats. indicating American aircraft manufacturers cooperated to ensure equipment from different suppliers could integrate successfully. Boeing built B-17s, Consolidated built B-24 Liberators, and eventually other heavy bomber types all employed similar autopilot interfaces, allowing standard Norden installation. This interoperability reflected coordination across organizational boundaries, with prime contractors and equipment suppliers agreeing on interface specifications early in development programs. German aircraft development generally proceeded with greater independence between airframe manufacturers and equipment suppliers, sometimes creating integration challenges when equipment designed for one aircraft type proved difficult to adapt to other platforms. The systematic interoperability evident in American bomber equipment suggested more centralized program management, imposing common standards across industry. The captured Norden's maintenance requirements revealed another dimension of American military-industrial organization that impressed German analysts. The technical manual specified scheduled maintenance intervals including lubrication points, inspection procedures, and component replacement recommendations based on operating hours. This preventive maintenance philosophy assumed sufficient spare parts availability and trained personnel to perform routine servicing, preventing failures rather than reacting to breakdowns. German military maintenance doctrine relied more heavily on corrective maintenance, repairing equipment after failures occurred, partly from necessity given spare parts shortages, but also reflecting different assumptions about resource availability and personnel training levels. The parts catalogue accompanying the technical manual listed hundreds of individual components, with part numbers, descriptions, and authorized replacement procedures. Many components were designated as line-replaceable units that maintenance personnel could swap without specialized tools or extensive training. This modularity enabled rapid repairs by replacing failed assemblies rather than diagnosing and fixing problems at the component level. Failed modules returned to depot facilities for detailed repair or salvage, while operational units received working replacements from supply stocks. This system maximized equipment availability and simplified field maintenance, but required substantial investment in spare parts, inventory, and reverse logistics to return failed components for repair. Germany's strained logistics networks increasingly struggled to support even basic maintenance by 1944, making such sophisticated support systems impossible to implement regardless of their theoretical advantages. German test pilots at Rechlin attempted to evaluate the Norden's operational effectiveness by installing it in captured B-17s and conducting simulated bombing runs over German ranges. These tests provided limited data since replicating combat conditions, including formation flying, anti-aircraft fire, and fighter opposition, proved impossible in test environments. But even controlled testing demonstrated remarkable accuracy potential when skilled operators used the equipment correctly under ideal conditions. Drops from 25,000 feet placed practice bombs within 200 feet of aim points consistently, performance that exceeded German bombsight capabilities at comparable altitudes by substantial margins. More significantly, test flights revealed how the automated system reduced operator workload during critical phases of the bombing run. Once the bombardier established tracking and engaged the automatic mode, the bombsight controlled the aircraft and calculated release point without further operator intervention. The bombardier monitored the system and could override if necessary, but normally he simply waited for automatic release. This automation reduced opportunities for human error during the high-stress final moments before bomb release, when manual bombing required the bombardier to maintain precise tracking while simultaneously calculating release timing and commanding the pilot to maintain exact heading. The Norden's automation handled these multiple tasks simultaneously with mechanical precision that humans couldn't match under pressure. German bombardiers who evaluated the system reported mixed reactions. Some appreciated the automation and recognized its accuracy advantages. Others expressed concern that relying on mechanical systems reduced the bombardier's skill, importance, and limited tactical flexibility if situations required deviating from planned approaches. These reactions reflected broader cultural attitudes about technology's appropriate role in warfare with some German military professionals uncomfortable with automation that seemed to diminish individual expertise and tactical judgment. The Americans apparently held different views, accepting reduced individual discretion in exchange for systematic performance improvements across large numbers of crews with varying skill levels. By summer 1944, the strategic situation had deteriorated so completely that theoretical discussions about bombsight capabilities became academic exercises disconnected from operational reality. The Normandy invasion in June established Allied forces in Western Europe, opening a new front that stretched German resources beyond sustainable limits. Soviet offensives in the east drove German forces back toward the pre-war border, liberating occupied territories and destroying entire German army groups. In Italy, Allied armies advanced northward, tying down German divisions that might have reinforced other fronts. And overhead, Allied bombers ranged across German skies with near impunity, systematically destroying war industries, transportation networks, and petroleum facilities. The Luftwaffe had been bled white defending against the daylight bombing campaign during 1943 and early 1944. German fighter losses exceeded replacement capacity, creating a downward spiral where declining fighter strength allowed bomber formations to penetrate with fewer losses, enabling expanded bombing campaigns that further degraded German fighter production and training facilities. The introduction of long-range fighter escorts, including P-51 Mustangs in late 1943, eliminated the altitude sanctuary, where German fighters had previously engaged bombers without fighter opposition. By mid-1944, American bomber formations routinely operated over German targets with massive fighter escorts that outnumbered and outperformed Luftwaffe defenders. Under these circumstances, whether German bombers possessed precision bombsights comparable to the Norden mattered not at all to operational outcomes. German bombers had been driven from daylight operations, forced into night harassment missions against tactical targets, where precision made little difference. The few remaining Luftwaffe bomber units operated under severe constraints, including fuel shortages, pilot training deficiencies from truncated instruction programs, and mechanical unreliability from overworked aircraft receiving inadequate maintenance. German bomber crews in late 1944 faced challenges far beyond bombing accuracy, struggling simply to survive missions against overwhelming Allied air defenses. The broader pattern revealed through examining the Norden and countless other pieces of captured American equipment centered on systematic industrial organization operating at scales Germany couldn't approach. American war production didn't just manufacture more equipment, it manufactured better equipment more consistently, while simultaneously developing next-generation systems and training personnel to use them effectively. This comprehensive military-industrial capability reflected decades of investment in manufacturing infrastructure, education systems, producing engineers and skilled workers, resource access from global supply networks, and economic capacity to sustain massive war production while maintaining civilian living standards. Germany had mobilized impressively for war, converting civilian industries to military production and achieving remarkable output growth between 1939 and 1944, despite increasing Allied bombing. But German mobilization started from a smaller base and operated under greater constraints, including strategic material shortages, limited energy resources, vulnerable supply lines, and most critically, multi-front war demands that dispersed resources across competing priorities. German industry produced sophisticated weapons and achieved impressive efficiency gains through rationalization programs, but the fundamental disparity in resource availability and industrial scale determined outcomes regardless of German technical competence or determination. The Norden bombsight represented one small manifestation of these larger patterns. American engineers had identified precision strategic bombing as a strategic requirement, invested over a decade developing comprehensive technical solutions, refined the capability through extensive testing, scaled production to equip thousands of aircraft, trained sufficient personnel to operate and maintain the systems, and integrated the capability into coherent operational doctrine, executed by massed formations operating from secure bases. Each element of this system, from bombsight technology to crew training to operational doctrine reinforced other elements, creating synergies that multiplied effectiveness. German approaches to military technology development typically proceeded less systematically, with different services and manufacturers pursuing parallel developments with limited coordination. Individual programs sometimes produced outstanding results, but comprehensive capabilities integrating multiple technologies with supporting doctrine and training structures emerged less frequently. The Norden demonstrated what systematic military technological development could achieve when organizations with clear requirements, adequate resources, and sufficient time pursued coherent programs across multiple reinforcing dimensions. By early 1945, Rechlin itself came under threat from advancing Allied forces. The testing facility had operated throughout the war, examining captured Allied equipment and evaluating German prototype developments. But the approaching end made continued operations increasingly difficult. Personnel received orders to evacuate valuable equipment and destroy sensitive materials before Soviet forces arrived. The captured Nordens and other Allied equipment were either destroyed by German personnel or fell into Soviet hands when the Red Army overran the facility in April 1945. Hauptmann Werner Baumbach survived the war and continued aviation career during the post-war period. He had written extensively about captured Allied aircraft and equipment during his wartime service, providing technical intelligence that informed German understanding of enemy capabilities, even when that understanding couldn't change strategic outcomes. After the war, his expertise made him valuable to Allied intelligence services, investigating German wartime technical achievements and assessing potential applications of German research to Cold War military requirements. He participated in multiple projects documenting Luftwaffe operations and German aviation technology development, contributing to historical understanding while carefully avoiding political controversies about the Nazi regime he had served. The Norden bombsight itself continued service with American forces through the war's conclusion, equipping B-17 seconds, B-24 Liberators, and eventually B-29 superfortresses in operations against Japan. The device proved effective when used by well-trained crews operating in permissive environments with fighter escort and limited anti-aircraft opposition. Under ideal conditions, the Norden achieved remarkable accuracy, with formations placing significant percentages of bombs within circular areas 500 feet in diameter from 25,000 feet. In practice, combat conditions, including weather, smoke, anti-aircraft fire, and fighter opposition degraded accuracy below theoretical capabilities, but the bombsight still enabled precision attacks on strategic targets that justified the investment in its development and production. Post-war analysis of strategic bombing effectiveness revealed complex patterns that defied simple assessments. American precision bombing attacks damaged German war industries significantly, particularly petroleum production and transportation networks. But Germany maintained substantial industrial output through 1944, despite sustained bombing, demonstrating both industrial resilience and the difficulty of achieving decisive effects through air power alone. The bombing campaign consumed enormous Allied resources, including tens of thousands of heavy bombers, hundreds of thousands of trained aircrew, and supporting infrastructure from bases to maintenance facilities. Whether these resources might have been more effectively employed through alternative strategies remained controversial among historians and military analysts for decades. What remained undeniable was the Norden's role as a symbol of American industrial and technological capability during World War II. The device embodied systematic approaches to military technology development, precision manufacturing at scale, and comprehensive integration of technologies into operational systems. German engineers examining captured Nordens recognized these characteristics and understood their implications for relative industrial capabilities between Germany and the United States. The bombsight itself was merely one component of the larger system that included aircraft, crews, bases, logistics, and doctrine, but its sophistication revealed the depth of American commitment to precision strategic bombing as a warfighting capability. The broader lessons from the Norden examination extended beyond immediate military applications to principles about industrial competition and technological development. The device demonstrated that achieving technological superiority in complex systems required sustained investment over long periods, comprehensive engineering across multiple disciplines, manufacturing capabilities to produce precision components at scale, and organizational structures to integrate diverse technologies into functional systems. These requirements favored nations with large industrial bases, substantial resource access, advanced educational systems, and the economic capacity to sustain long-term development programs. Germany in the early 1940s possessed technical expertise and engineering talent comparable to any nation, but lacked the comprehensive industrial capacity and resource access that enabled American military technological achievements like the Norden. Individual German engineers and institutions produced remarkable innovations across multiple technological domains, from jet engines to guided missiles to advanced optics. But Germany's smaller industrial base, strategic material constraints, and multi-front war demands limited their ability to transform technical excellence into decisive military advantages through sustained mass production of mature systems. The Norden bombsight story illustrated how modern warfare had evolved beyond individual technical superiority to comprehensive industrial technological competition, where systematic organization mattered more than isolated innovations. The most sophisticated individual weapon design couldn't overcome fundamental disadvantages in industrial capacity and resource availability. Victory required not just good designs, but the manufacturing capability to produce them in quantities sufficient to equip forces across multiple theaters, the logistics to maintain them in field service, the training systems to produce qualified operators, and the operational doctrine to employ them effectively. German technical intelligence by 1945 had accumulated vast documentation about Allied equipment capabilities through examination of captured materials. Officers and engineers understood their adversaries' technological achievements and recognized the industrial capabilities those achievements represented. But this knowledge provided no path to reversing strategic outcomes determined by comprehensive disparities in resources and production capacity. Understanding why you were losing didn't create resources or capabilities to prevent defeat when fundamental limitations couldn't be overcome through any realistic means. The Norden bombsights captured at Rechlin and elsewhere during the war became footnotes in history, interesting technical artifacts that revealed aspects of wartime industrial competition but didn't determine strategic outcomes themselves. The devices taught German engineers about American capabilities, confirmed suspicions about industrial disparities, and provided case studies in systematic military technology development. But the lessons came too late and under circumstances where they couldn't influence Germany's trajectory toward comprehensive defeat. In the decades following the war, the Norden bombsight faded from public consciousness as newer technologies rendered mechanical computing obsolete. Radar bombing systems, inertial navigation, and eventually satellite-guided precision weapons superseded optical bombsights like the Norden. By the 1960s, the device that had represented cutting-edge technology in 1943 became a museum piece, interesting primarily to historians and technology enthusiasts studying World War II-era military equipment. But the principles embodied in the Norden's development remained relevant to understanding military-industrial competition in the modern era. The device demonstrated how comprehensive capability required integration of multiple technologies, how manufacturing precision at scale provided decisive advantages, how systematic development over extended periods produced mature systems superior to hastily improvised alternatives, and how industrial organization mattered as much as technical innovation in determining military technological outcomes. For German engineers who examined captured Nordens during the war, the device represented both an intellectual challenge and a sobering confirmation of strategic realities they increasingly couldn't escape. The sophistication impressed them professionally even as its implications depressed them strategically. Here was tangible evidence that their adversary possessed industrial capabilities exceeding German capacity by margins that no amount of technical cleverness or determination could overcome. The precision machining, the sophisticated design, the systematic integration, all pointed toward industrial organization operating at scales and efficiency levels that Germany couldn't match. Some of these engineers, like Baumbach, recorded their observations in technical reports that survived the war, providing historical documentation of how German technical experts assessed Allied capabilities. Reading these reports decades later reveals the tension between professional admiration for impressive engineering and recognition that such capabilities boded ill for Germany's strategic prospects. The engineers couldn't directly state that defeat was inevitable, but their technical assessments implicitly communicated the message through documented capability gaps and resource disparities that careful readers understood couldn't be closed through any realistic German efforts. The story of the Norden bombsight examination at Rechlin in 1943 and 1944 represents a small episode in the vast canvas of World War II, a technical intelligence operation that provided information without changing strategic trajectories. But the story illuminates larger patterns about industrial warfare, technological competition, and the relationship between manufacturing capabilities and military outcomes. The device itself was remarkable, embodying 15 years of systematic American development in precision bombing technology. But more remarkable was the industrial system that produced thousands of these sophisticated mechanisms while simultaneously manufacturing countless other war materials, from ships to tanks to aircraft to electronics, all at scales that overwhelmed Axis production despite determined resistance. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.